So we are looking at root locus, right? So we completed 2 steps. So first step is to locate the open loop poles and open loop 0 in the complex plane, and then the second step was to locate the parts of the real axis that lie on the root locus, right? So those are the 2 steps, okay, that we have completed till now. And today let's start from step number 3. Like step 3 deals with determining the asymptotes, okay, like of the root locus, okay. So obviously this step applies only when m is less than n. So if you recall what were m and n, small m was the number of zeros, right, open loop zeros, small n was the number of open loop poles. So as we discussed, like each of the root locus will have n branches. Each branch will start from an open loop pole, and m branches will terminate at the m zeros, open loop zeros, as k tends to infinity, and the remaining n minus m branches will go to infinity along asymptotes. So obviously asymptotes are going to exist only when n is strictly greater than m, okay. So what really happens, right? So let me take the same example, since we are doing this example where n is equal to 2 and m is equal to 0. So we are going to have n minus m asymptotes, right? That means we are going to have 2 asymptotes, correct? So now let's say, like by definition, asymptotes means, like what is the trace of the root locus or the closed loop poles as k tends to infinity, right? That's the meaning. So let's say you push the test point st away towards infinity, right, farther and farther away from the origin. What do you think will happen to theta 1 and theta 2? Like any point, any direction, doesn't matter. So in the limit, as st goes to infinity in any direction, what do you think will happen to theta 1 and theta 2? They will become equal, right? So it doesn't matter, right, which direction you push it in, right? So let's say st, you push it to infinity, right? So let's say somewhere even towards the top left here, right? So as st tends to infinity, you draw the vector from -4 to st and 1 to st, like the angles are almost going to converge to the same value, right, in the limit as st tends to infinity, right? So it doesn't matter which direction we go. So you see that the angle contribution from each open loop pole and each open loop 0 would become equal. Do you agree? So that is how we get this equation, okay. So if the test point is chosen very far away from the origin, then the angle contribution of each open loop pole cancels with that of an open loop 0, right, because the phase contribution cancels off, right, between the open loop pole and the open loop 0, because they are equal in magnitude, right. So hence the asymptotes will be straight lines which make an angle with the positive real axis of plus or minus 180 degrees times 2k plus 1 divided by n minus m, right. So because n minus m would be the difference, right. So if I go to this file, so here we did not have a 0. So what did we get? If theta 1 is equal to theta 2, let us say if theta 1 is equal to theta 2 as st tends to infinity, what will happen to, let's say, like theta asymptote, that's going to be equal to plus or minus 180 degrees times 2k plus 1 divided by 2, right, because you are going to get 2 times theta asymptote on the left hand side, right. But if there were a 0, what would happen? You would have another theta, right, before that, right. So you get the point, right. So the denominator 2 came here because that was n minus m, right. So here m was 0. So please note that here n minus m is going to be equal to 2. Okay, so that's why we got n minus m in the denominator. Why? Because we want to satisfy the angle condition. So once again we keep on coming to this condition, right. So essentially most of the steps in the construction of the root locus depend on the angle condition, right. So that's why we use this formula. Is it clear? So let me go back to the PDF file. So the asymptotes which exist only when m is less than n will be straight lines which will make an angle with the positive real axis of plus or minus 180 degrees times 2k plus 1 divided by n minus m. Okay, so that's the angle made by the n minus m asymptotes with the positive real axis, right. So that's what we have. And the point of intersection of the asymptotes on the real axis is given by this formula, which is the same as calculating sum of the open loop poles minus the sum of the open loop zeros divided by n minus m. Okay. How do we get this formula? I leave it to your homework, right? So you think about it, right? So once again, like what are asymptotes? Asymptotes essentially indicate the trace of the closed loop pole as the test point st tends to infinity, right? Now you ask yourself the question, like what will be the root of the closed loop characteristic polynomial as st tends to infinity in general, right? So as the test point tends to infinity, what would be the root, okay, of the closed loop characteristic polynomial, right? And what condition do you need, right? So how will such asymptotes intersect on the real axis? And one can show that that point of intersection is going to be sum of open loop poles minus sum of open loop zeros divided by n minus m. Okay, that is the formula. Once again, like as I told you, that part I am going to leave it to your homework, right? How to figure it out is homework for you. So we figured out, like how to get the angle of intersection of the asymptotes, right? So that's coming from the angle condition. So let me go back here. So step 3. If we start step 3 here, so step 3 deals with the asymptotes, the evaluation of the asymptotes. Okay, so the angle of first of all, here in this problem n minus m is going to be equal to 2 minus 0, which is 2, right? So this implies that there are 2 asymptotes in this problem. Okay, so the angle of intersection, or I am sorry, not angle of intersection, angle made by the 2 asymptotes, okay, is going to be equal to plus or minus 180 degrees times 2k plus 1 divided by n minus m, right? So this we are going to get it as plus or minus 90 times 2k plus 1, right? K going from 0, 1, 2 and so on. So I can, in this case, like I can write these 2 numbers as plus 90 degrees and minus 90 degrees. Minus 90 degrees is the same as saying 270 degrees, right? You can count it anyway, right? So if minus 90 means you count, you start from the positive real axis, go 90 degrees in the clockwise direction. So that's essentially plus 270, right? You start from the positive real axis, go counterclockwise by 270 degrees, right? So that's the same thing. So the 2 asymptotes, if I have to draw the 2 asymptotes, what's going to happen is the following. So if I plot the real axis and the imaginary axis, and this is my S plane, the 2 asymptotes are going to make plus 90 and minus 90. Please remember, we have an open loop pole at minus 4 and open loop pole at plus 1, right? So that's our base system. Now, the point of intersection of the 2 asymptotes on the real axis is going to be, as we looked in the step, it's going to be sum of open loop poles minus sum of open loop zeros divided by n minus m, right? So that's the easiest way to remember it. So if you recall, what were the open loop poles? Open loop poles were minus 4 and plus 1. That's why I always suggest that you follow this process so that we would not make a mistake, right? So you always write things clearly so that there is no confusion, right? And if you look at the open loop zeros, there were nil. Okay, so what happens is then you have minus 4 plus 1, okay, and that's the sum of open loop poles minus the sum of open loop zeros. There are none. Okay, I just write 0. Okay, I could have left it empty, but I am just writing it 0 divided by n minus m, which is 2. So what's the answer? Minus 1.5, right? So at minus 1.5, I am going to have the 2 asymptotes meet each other, and the angle, one asymptote is going to essentially go like plus 90, another asymptote is going to go like minus 90. Okay, so these are the two asymptotes. Okay, so I hope it's clear what this is, right? So let's say we call this as asymptote number 1. Okay, this as asymptote number 2.
Sir,
yes, please.
there seems to be a typo here where it says point of intersection of asymptotes is given by minus of sum of open loop poles.
Yeah. See, please remember, open loop poles are minus P1, minus P2, minus Pn. So you take the minus sign inside, right? Okay. So yeah, I hope I typed it correctly, right? Did I call minus P1, minus P2, minus Pn as the open loop poles, right? So yeah, it really depends on how we write it, right? So let me scroll up. Yeah, okay. So I didn't write. See, if I had written S minus P1, P1, P2, Pn would have been the open loop poles. Since I wrote S plus P1, minus P1, minus P2, minus Pn are the open loop poles, right? So I hope this is correct. So I take the minus sign inside, yeah, right? So this formula becomes easy. So I prefer that you remember this formula because it's easier. So you write open loop poles, sum everything, and then sum all the open loop zeros, subtract, and divide by n minus m. It's easier to remember. Okay, so that's why I suggested this formula, right? Okay. So that's essentially calculation of asymptotes. So if you recall, what we have done till now is that we have figured out that like two branches are going to be there. One is going to start from minus 4 towards the right and one towards the left, and the region between minus 4 and plus 1 is the part of the root locus that lies on the real axis. And then the third point that we have figured out that there are going to be two asymptotes which intersect at minus 1.5 and they just go plus 90 and minus 90. Please remember, the asymptotes indicate the trace of the root locus as essentially k tends to infinity, right? So that's what it means, right? So okay, so those are the first 3 steps. Okay, so let's go to step 4. Okay, so what is step 4? Okay, so step 4, let's first read through it. Okay, then we will discuss. It says determine the breakaway points and break-in points. Okay, so I'll explain to you what a breakaway point and what a break-in point is, right? So a breakaway point, for example, will exist on the root locus between two successive open loop poles on the real axis with no real open loop zeros in between them. Okay. Similarly, a break-in point, for example, will exist on the root locus between two consecutive open loop zeros on the real axis with no real open loop poles in between them. Okay, that's how you should read the sentence. Okay, you take the pair of words within the parenthesis and outside the parenthesis as a set, right? So let me explain to you what it means. Suppose, like as in this example, so I am looking at now step 4. Let's say I write in blue. Okay, so we are looking at step 4. Step 4 involves calculating what are called breakaway or break-in points. Okay, so that's step 4. Okay, so let's look at that. So when will I have a breakaway point? See, for example, let us say I have the real axis. Okay, so I am just looking at the real axis. Let us say this is my imaginary axis. Okay, suppose let us say like in this example I have minus 4 and 1. So these are two open loop poles on the real axis, okay, without any open loop 0 in between, right? And what did we discuss? Like as far as this particular example is concerned, I'm going to have one branch starting from minus 4 and coming to the right, one branch starting from plus 1 and coming to the left. Okay, so as k keeps on increasing from 0, so please note that my root locus will start at the open loop poles as k tends to 0, right? So that is the first point, right? As k keeps on increasing, this branch is going to come towards the right, this branch is going to come towards the left, and at some point they are going to meet each other. Is it not? Do you agree? Because one branch is coming to the right, one branch is coming to the left. Okay, and at this point they are going to break away from the real axis, because obviously I cannot turn back or cross each other, right? See, because I cannot have like the two branches going anywhere other than like going into the complex plane, right? Because I have already covered the real axis, they are just hitting each other and they will just break away, right? So they may just break away as complex conjugate roots. Now they can break away, right? Because a complex root will have conjugate also as a root, right? So there are two branches which essentially hit each other and just break away from the real axis. Okay, so this is what is called as a break away point. Okay, so I hope the meaning of a breakaway point is clear. Okay, so this need not always happen, but in this example it happens, right? So that's why I wrote for example. Similarly, like if we had a scenario, I'm just giving an example, okay, where let us say I had two zeros, let's say one at -3 and one at -6, okay, correct? And there are other open loop poles and open loop zeros and so on, right? But there are two open loop zeros on the real axis at -3 and -6 with no open loop poles in between them, right? What would happen? What do we know from our analysis? We know that the root locus will tend to the open loop zeros as k tends to infinity. Suppose there were a case where one branch comes in and terminates like this, and another branch comes in and terminates like this as k tends to infinity. As you keep on decreasing k, they will travel towards each other, and at some point they would have hit each other and then they might have gone something like this. Okay, so but this is the direction of travel, right, isn't it? So this is what is called as a break in point. Okay, it breaks into the real axis. Okay, that way you can remember it. Here it breaks away from the real axis. Okay, that's why it's called as a break away point. Okay, I hope it's clear what is the meaning of a break away point and a break in point. Okay, now how do we calculate these breakaway and break in points? As you do more examples, this will become clear. Okay, it's not always necessary. I'll give you an example at the homework at the end of today's class where it will become clear to you as to why like you need not always have a breakaway point, even the example that we are doing. See, for example, when k is non-positive for the other case, you will see that this does not happen, right? So we'll discuss all those things as we go along. But what is one unique feature about a breakaway or a break-in point? Doesn't matter whether you are considering a breakaway point or a break-in point. What really happens at that point? Two branches intersect, right? So at the same value of k, what can you say about the closed loop poles? See, each branch of a root locus indicates the locus or trace of a closed loop pole, right, as k goes from 0 to infinity for us, right? So let's say, like one branch starts like this from -4, another branch starts from +1, and they come and intersect each other at some point on the real axis, right? So for that particular value of k, you are going to have a repeating pole, would you not? Because the same point in the S plane would be a root, because you have two branches coming and intersecting each other. Now I asked you a question, I think 2 classes ago, right? I left you with a question. If you have a polynomial which has a repeating pole, like what characteristics can you extract from it? Let's go as an aside, right? So let's say I have a polynomial d1 of s, which is s plus 1 times s plus 2. Right? I have another polynomial d2 of s, which is s plus 1 whole square times s plus 2. Right? So in the second polynomial, -1 is a repeating root, right, with multiplicity of 2. Now what is what characteristic can you or attribute can you extract out of this? Of course, a root of a polynomial means when you substitute the value should be 0. But what is unique about a repeating pole? See, let's say, like I take the derivative of d1 with respect to s. d1 prime means I am taking the first derivative, right? What will I get? I will get s plus 1 plus s plus 2. Am I correct? Do you agree? Right? Now, if I take d2 prime s, what will I get? I will get 2s plus 1 times s plus 2 plus s plus 1 whole square times s plus 2. sorry, s plus 1 whole square, right? That's it. So this should give you the answer, right? So when you, since minus 1 has a multiplicity of 2, the first derivative is also 0, right, in D2. So you substitute minus 1 in the, what to say, first derivative of the polynomial. Since minus 1 is a repeating root for D2, it makes the first derivative also 0. But you see that minus 1 was not a repeating root in the first polynomial D1. You substitute minus 1 in D1 prime, that's not 0, right? You get 1 as the answer, correct? So if you have a, in general, if you have a root to have a multiplicity of mu till the mu minus 1 derivative, the derivative would be made 0 when you substitute that repeating root, right? Correct? If you take the second derivative will not be 0. You can easily check it. You can easily double check that one, right? So so irrespective of the multiplicity, how many times it repeats, all of us agree that if the multiplicity is greater than 1, first derivative is going to be certainly 0. We make use of that fact, right? So is it clear what logic we are going to use now? Okay. So let for this particular case, let g of s h of s be written as k times a of s divided by b of s, okay, just for simplicity. So if you recall, a of s is nothing but s plus z1 all the way till s plus zm, okay, and b of s is going to be equal to s plus p1 all the way till s plus pn, okay. So and consequently the closed loop characteristic equation is going to be 1 plus k times a of s divided by b of s is equal to 0. Do you agree? That's what is going to be the closed loop characteristic equation, because what is closed loop characteristic equation? It is 1 plus g of s h of s equals 0. Now if the closed loop characteristic polynomial has a repeating root, immediately what can we say about it? Derivative is going to be 0, right? So my closed loop characteristic polynomial, let me call it as PCLS, is going to be equal to of course 1 plus k a of s b of s, right? So this implies that the derivative prime, what I mean by prime is nothing but dPCLS ds, okay, that's what is the meaning. That's going to be equal to plus k, and then like what do I have? I have bs square, and then we have a prime s bs minus b prime s as is equal to 0, right? Do you agree? Okay. So consequently, obviously, you know, like we don't have k to be 0, right? We can't have k to be 0 because k to be 0 means, you know, like anyway we don't have a problem to begin with, right? The open loop transfer function will become 0, right? So and obviously at this breakaway break-in points, you know, like we don't have b of s to be 0 either. Why not? We are not considering scenarios where b of s is 0. What do you think will happen when b of s is 0? You tend to the open loop poles, right? Open loop poles means anyway k is, that's where the root locus starts. So we eliminate the scenarios where k is 0 and b of s is 0. So what should be 0? Sorry, b of s being infinity, sorry, okay. So what should be 0? The numerator, right? So a prime s b of s minus b prime s a of s is equal to 0. Okay, let me repeat that. You know, like we don't want k to be 0, right? We cannot have k to be 0, first of all, right? You know, like it's not that we don't want, we can't have k to be 0 from this equation, right? Because there are three terms, right? K, what is within the parenthesis, and b of s. If b of s tends to infinity also, this can be 0, but why can I not have b of s tending to infinity? What is b of s? It's s plus p1 all the way till s plus pn. When do you think that will tend to infinity? S tends to infinity, but we are looking for breakaway break-in points on the real axis which are finite, so we eliminate that possibility, right? So what is the only possibility? The term within the parenthesis being 0. So what we do is that we solve this equation, okay? The roots of this equation, okay, are potential breakaway break-in points, okay? Why am I saying potential, right? So we will see why, right? So, but then we still need to do one more check. What we need to do is that we need to figure out the value of k corresponding to these points and check whether they are positive, okay? Then only those points will lie on the root locus, okay? So let me repeat what I meant just now. You solve this equation, you get some values of s, right? Then find or calculate, let's say, we call these roots of this equation as some SB, okay? I am just putting a subscript B, okay, to indicate breakaway or break-in points. Then calculate the values of k as minus b of s divided by a of s evaluated at s equals SB, okay? Only those values of SB that result in k greater than 0 would lie on the root locus, okay, for our scenario. Okay, so there are two steps. First you solve this equation, then you find the corresponding values of k. How did I get k equals minus b of s divided by a of s? From the closed loop characteristic equation, right? So you just rearrange the terms, right? You get the values of k, right? An expression for k, right? So we need to do both these steps. Is it clear? Okay. So now let's come to our example, right? In our example, what were the expressions for a of s and b of s? The example that we are doing. Because you can also have sometimes, like negative values of k, which are not allowed. That means that those roots do not lie on the root locus for our case, because we are considering only positive k. Okay, so there can be even like other values of k which do not make sense. Like you can have complex conjugate k, for example, right? You can have arbitrary other roots, like which do not essentially satisfy our conditions. Okay, so because we are only looking at the case where k is positive. Okay, because it gives you in general points where you can have multiple roots, right, for the given polynomial. Okay, but considering our case, like we are checking for only those scenarios where k is greater than 0.